Now, let us find out the lower cutoff frequency due to the coupling capacitor C2 and ignore the other two capacitances. The circuit of the amplifier having the coupling capacitor C2 only will be looking like this circuit, where the capacitor C2, which is at the output side, it is coupling the output signal basically. So, the circuit is having the other portion almost same like the mid frequency region analysis. So, we can find out what will be the gain from Vs to V naught dash, where the V naught dash is the voltage at the terminals A B just before the capacitance C2. So, separating this part from the output side where we have this capacitance C2 in series with the load resistance RL, let us find out first V naught dash by Vs. That we know, we are familiar with the voltage gain, that is equal to minus R in by R in plus Rs into beta times of Rc by beta plus 1 Re. We do not consider the output resistance R naught, that is why only Rc, which is the output resistance, it is R naught equal to Rc. So, V naught dash by Vs is this quantity. Now, let us consider the output side circuit having this voltage at V naught dash and the rest of the circuit. So, V naught dash is equal to minus Vs into R in by Rs plus R in into beta Rc by beta plus 1 Re, that is from this expression we are having here the voltage V naught dash. It is having a resistance R naught in series, that resistance is the output resistance, which is nothing but Rc. So, the whole left side of this circuit from A B is having the voltage V naught dash in series with R naught, and the rest of the circuit will be connected there. So, the rest of the circuit means to the right of A B we have C2 and RL. Now, in this circuit we can find out what is V naught at this point. So, V naught equal to the voltage across these 2 points, which is having the resistance RL. So, V naught equal to V naught dash into RL divided by RL plus this series resistance and capacitance. So, the denominator will be RL plus R naught plus 1 by j omega C2. So, that is the output voltage finally we get here. Now, we find V naught equal to V naught dash into this quantity, which can be further simplified. So, now we will take the ratio between V naught and V naught dash, that is equal to RL by RL plus R naught can be replaced by Rc, because if we look into the circuit, R naught, the output resistance, when I look from the output terminals, it is nothing but only Rc, because Vs has to be short circuited and that makes this IB 0. So, we have only Rc across it, that is the output resistance R naught. So, replacing that R naught by Rc, we get in the denominator again I am writing this quantity by minus j by 2 pi f C2. So, simplifying a little further, taking common RL plus Rc in the denominator, I get 1 minus j by 2 pi f RL plus Rc into C2. So, V naught by V naught dash equal to RL by RL plus Rc into 1 by 1 minus j into 1 by 2 pi f RL plus Rc into C2. This quantity can be written as 1 by 2 pi into RL plus Rc into C2 divided by f. So, replacing this whole quantity 2 pi into RL plus RC into C2 by FLC2 divided by F we get in the denominator, and so the FLC2 which we are denoting by this 1 by 2 pi into RC plus RL into C2. Now, we will be finding out the overall voltage gain V naught by Vs using the chain rule. It is V naught by V naught dash into V naught dash by Vs. Now, V naught by V naught dash just now we have found out. So, we will be replacing by this quantity here RL by RC plus RL into 1 by 1 minus J FLC2 by F, and the rest of the quantity, that is V naught dash by Vs, we know that is equal to minus R in by Rs plus R in into beta RC divided by R beta plus 1 into Re. Now, the whole expression of V naught by Vs will be equal to minus beta into Rc by beta plus 1 into Re, then this whole quantity written together. So, this is the overall expression. Now, if we look into this numerator, the portion Rc into RL by Rc plus RL, that can be written as Rc parallel RL. So, in the numerator we have minus beta into Rc parallel RL divided by beta plus 1 Re, as it is we will be writing. The rest of the part is R in by Rs plus R in into 1 by this quantity. So, we can write AVSF as equal to this quantity of minus beta Rc parallel RL divided by beta plus 1 Re into R in by Rs plus R in. This is nothing but the voltage gain AVS in mid frequency region. So, that is nothing but I naught, and the rest of the term will remain. Now, if we consider only the magnitude of AVSF, it is the magnitude of A naught into 1 by root over 1 plus FLC2 by F whole square, because that part is the magnitude of the complex quantity. Now, when the frequency F becomes equal to FLC2, then in the denominator we will be having only 1 plus 1 root. So, that is equal to root 2. So, we have the magnitude of the voltage gain as 1 by root 2 times A naught. 1 by root 2 is nothing but 0.707. So, that is what we are getting if we make F equal to FLC2. That means it verifies that the lower cutoff frequency due to C2, which we have assumed as 1 by 2 pi into Rc plus RL into C2, because we have replaced here this FLC2, we are replacing for this quantity 1 by 2 pi into RL plus Rc into C2. Now, replacing that by FLC2 and further analyzing, we have finally got that when the signal frequency F becomes the frequency given by this quantity FLC2, then the gain reduces to 1 by root 2 times the mid frequency gain A naught. So, that verifies that the lower cutoff frequency due to C2 is equal to 1 by 2 pi into Rc plus RL into C2, and basically that is nothing but, if we look into the circuit and find out what is the effective resistance across C2 and then find out what is the time constant, from that we get the same lower cutoff frequency only. So, that is a very simple analysis, we can straightforward find out, and that is what we can get directly the lower cutoff frequency, which is equal to 1 by 2 pi into effective resistance across this capacitance into the capacitance. Now, what is the effective resistance across the capacitance? To find that, we have to look into the circuit from that capacitance, that means from this portion of the circuit we will be looking into, making this capacitance open. What will be the effective resistance? Making V naught dash of course 0, we will be left with this two resistances in series, because this is the capacitance C2, this is R naught which is equal to RC, and this is RL. So, when I look from these points across C2, I am having R naught and RL, that means RC and RL in series. So, that means I get the effective resistance for this capacitance C2 as RC plus RL into C2. So, from this I get the cutoff frequency, because this is nothing but the time constant, R into C is time constant. So, from that you get the cutoff frequency. Actually, from this whole analysis we are finally ending up in getting that frequency only, which is the frequency obtained for C2. Now, if we find out the effect of CE, that is the bypass capacitor across the resistance RE. Considering only CE and ignoring the other coupling capacitors C1 and C2, we will be finding out the lower cutoff frequency due to CE. So, what will be the circuit now? The circuit will be having CE, but the other capacitances will be absent, because that we are assuming a short circuit. So, now this capacitance CE is there. So, we are to find out what will be the lower cutoff frequency due to this capacitance. The easiest way we will be now adopting that we will find out what is the effective resistance across this capacitance CE. So, in order to know the effective resistance across this capacitance CE, we just remove this capacitance, open circuit it. I mean, this at this point we are just disconnecting this CE and look into the circuit to find out the effective resistance. So, that is what we are doing here. The resistance across this capacitance CE can be now found out, which is say R naught, and R naught which we will finding out across these 2 points will be in parallel with RE. RE is there, but we have to find out at these 2 points A, B, what is the output, what is the resistance R naught looking from this terminals A, B, and that resistance R naught, if it is in parallel with RE, that will be the effective resistance due to CE. So, in order to find that out, we will be finding out the resistance of this left side circuit from this AB terminals. So, for that we apply an external voltage Vx. This external voltage will be making a current flow in the circuit. One part will go through this, one part will go through this circuit, right, to the right, and mind it, we have made Vs is equal to 0, because the independent source has to be made 0. When you have to find out the effective resistance across these 2 terminals, you make the circuit inactive, means the independent source you make 0, but here actually we will have to apply an external source to know this output resistance looking into the circuit from this terminals AB, because there is a dependent current source and that source beta times of IB will be having one part of the current which is due to this external source. This is the way to find out the output resistance, and so because of this Vx, Ix current flows and one part goes to this side which is beta times of IB, where IB is the current flowing through this resistance. Now, the total current Ix is equal to then IB plus IC. IC is that current which is through the collector point, and through the base point IB current flows. So, that means Ix is equal to beta plus 1 into IB, because IC is equal to beta times of IB. So, that means we get that IB equal to Ix by beta plus 1. So, what is this voltage Vx now? Vx is equal to the drop across beta plus 1 Re plus this drop across these 2 points. Now, the drop across beta plus 1 and 1 into Re is equal to the current Ib into beta plus 1 Re. Again Ib is equal to Ix by beta plus 1 into beta plus 1 Re. So, this cancel, plus the voltage across these 2 points is current Ib which is flowing in this direction into the equivalent resistance between these 2 parallel resistances Rs and Rb. So, making that this part is equal to Ix by beta plus 1 which is this current Ib into Rb parallel Rs. So, now you take the ratio between Vx and Ix which is equal to R naught, that is equal to small Re plus Rb parallel Rs by beta plus 1. So, this is the effective resistance across this capacitance Ce. So, now we can easily find out the time constant associated with that capacitance Ce, which is R effective and Ce, and R effective we have just now found out to be equal to Re parallel this component. So, because we have found out R naught, but exactly what will be the effective resistance across this capacitance, it is Re parallel R naught. So, R naught is this component. So, effective resistance is equal to Re parallel this whole term, that will be giving the corresponding cutoff frequency as FLCE, which is 1 by 2 pi R effective and Ce. This is due to Ce. This lower cutoff frequency FLCE is due to the emitter bypass capacitor Ce. So, by finding out the effective resistance across each of the capacitor, we can straightforward we can find out the lower cutoff frequency associated with each of these capacitors. Now, we have found out there are 3 lower cutoff frequencies due to each of these capacitors. So, in order to find out the overall cutoff frequency of the amplifier, considering all the 3, we will take the largest value of all these lower cutoff frequencies. That means, out of FLC1, FLC2 and FLCE, we will be taking the largest value, and that is the overall or the final lower cutoff frequency of the amplifier. Now, after knowing the lower cutoff frequency, let us proceed to find out the upper cutoff frequency. Then we will be considering the amplifier in the high frequency region. So, as per our earlier analysis, in the high frequency region, the capacitances which will be having effect are the transistor junction capacitances, that is CBE, base to emitter junction capacitance, and CBC, collector to base junction capacitance. But the others, that is the coupling and bypass capacitors, will be now ineffective because they are almost like short circuit. So, now at high frequency region, again let us consider the overall amplifier circuit. So, in this amplifier circuit, now it is the overall circuit diagram having all the capacitances. Once again we are recalling that circuit. Now, the effective capacitances will be these two, because these capacitances are no longer open circuit, their capacitive reactances are smaller, so that a part of the base current is shunted out through these two capacitances. That is, out of the current which is coming into this point, one part will be shunted out through this capacitance, another part will be shunted out through this capacitance CBC, and the rest will be only flowing through the resistance beta plus 1 Re. That means, the current which is now flowing through this resistance and finally through this resistance, it will be not Ib as in the earlier case, but it will be a portion of Ib only, that is IB now is less than its earlier value when it was only in the mid frequency region. So, if IB is now reduced because of the shunting away by these capacitances, then obviously the collector current will also be reduced, beta times of IB will also be reduced. So, that is why the voltage gain V naught will be also reduced, because the voltage at the output is dependent on this current source. So, now we are considering the at high frequency, and we will be trying to find out what is the upper cutoff frequency. So, ignoring the effect of all other capacitances and keeping only the shunting capacitances due to the transistor, which are CBC and CBE, we are considering the circuit again. Now, in this amplifier circuit, as shown by this arrow marks of these currents, the input current which was coming, the input current has now 3 parts. One will be going to this CBE, one will be going to CBC, and the rest or the finally what is left only, that will be the base current. Now, in order to analyze this circuit, because we have a difficulty in analyzing the circuit, it is not a simple circuit because of this shunting capacitance CB is giving a problem, because it is now across these 2 points B and C. That means, this capacitance CBC is not allowing the whole circuit to be divided into input and output circuits, but there is a part from base to collector. So, this capacitance CBC, as it is shunting between base and collector, we are having a trouble for separating the input and output circuits out, because in order to analyze a circuit, it is better to have the input and output circuits separated out, but here the problem is coming because of the shunting capacitance between the input and output, that is base and collector. So, if somehow we can simplify this circuit further by separating out the input and output circuits, then it will be better for our analysis. So, in order to separate out the input and output circuits, we have to distribute this capacitance CBC in the input and output circuits and thereby removing it from this part. So, that can be done by taking help of a well known established theorem known as Miller's theorem. So, what is Miller's theorem and how we are going to apply it in this circuit to simplify it, that we will be discussing first. So, the Miller's theorem says that if we have a number of nodes, n being the node to ground, that is, this is the ground node, other nodes are 1, 2, 3, 4, there may be many nodes, the voltages being at these nodes are V1, V2, etc. And here there are the impedances or say Z we are considering only between these two nodes 1 and 2, say for example, to simplify and to analyze this or illustrate this point first. What is Miller's theorem? Let us take V1 and V2 at the two nodes 1 and 2 having an impedance in between them, which is Z. Now, the current I1 is flowing through Z from V1 to V2 and current I2 is flowing from V2 to V1. Now, we want to simplify the circuit, and Miller's theorem says that this Z, which is between V1 and V2, can be distributed between 1 and ground, that is node N, as well between 2 and ground, that is N. The corresponding values which will be between 1 and node will be Z by 1 minus K, where K is the voltage ratio between V2 and V1, that is the ratio between the voltages V2 and V1 is say K. Then we can distribute Z into the input and output circuits, removing it completely from this part between 1 and 2. to make the circuit easier or simpler. And the value of Z1 that is connected between 1 and ground will be Z by 1 minus K, the original value of Z divided by 1 minus K, K being V2 by V1, this ratio. And similarly, the value of Z2 which is between 2 and ground, this V2 and ground, that will be Zk by K minus 1. And then we can easily find out the current also. Now, these values of Z1 and Z2 as we are writing here can be verified actually. How we are getting the value of the resistance between one and n being Z1 by Z by 1 minus K and the other being Zk by K minus 1. That can be verified if we consider the currents in both the cases and make them equal. So, let us, because you see the currents are still I1 is flowing from V1 to ground, I2 is flowing from V2 to ground, and earlier this was the current I1 from V1 to V2. Now, these two are equivalent circuits. So, to prove the point that these two are equivalent circuits, let us proceed from the current. Let us find out what is current in this circuit. I1 equal to V1 minus V2 by Z, that can be written as V1 into 1 minus V2 by V1 divided by Z. Again, V2 by V1 is nothing but the voltage ratio K. So, we can write it as V1 into 1 minus K by Z, and again we can write it as V1 by Z by 1 minus K. So, finally, we are getting an expression which is V1 by Z1, Z1 for Z by 1 minus K we are writing, and this is the current which is flowing in this circuit. Now, similarly, if we find out what I2 V2 minus V1 by Z can be written as V2 into 1 minus V1 by V2 by Z, that is equal to V2 into 1 minus V1 by V2 will be 1 by K by Z, and that is equal to V2 by Z by 1 minus 1 by K. So, let us write it by V2 by Z2. Now, if we look into this quantity V1 by Z1, V1 is with respect to ground. So, we get the second circuit current which is V1 by this impedance which is Z1, nothing but Z by 1 minus K. That means, instead of writing I1 in this way, we have written it in this form. So, these two are equal, this current expression and this current expression, we are just writing it in a different way, but that can be realized in this circuit, because V1 by Z by 1 minus K means that this is the current where the voltage is with respect to ground, and that is what is here, V1 is with respect to ground divided by this impedance Z by 1 minus K, and that is the impedance which is in the path between voltage V1 and ground. Similarly, in the second case we are getting V2 by Z by 1 minus 1 by K, and that is nothing but this is the voltage with respect to ground, V2 is the voltage with respect to ground, and the denominator is having a value of impedance which is Z by 1 minus 1 by K. So, obviously, their impedance is between this node 2 and ground, which is Z by 1 minus 1 by K. Z by 1 minus 1 by K can be written as Z into K by K minus 1. So, from this figure we are proceeding, and finally, we are getting a circuit which is having the input and output sides separated out with respect to ground, but here it was having a shunted impedance in between the two nodes. Now, this theorem will be now applied to our amplifier for distributing the capacitance between base and collector and separating out the input and output side circuits. So, let us do that now. So, finally, we are having the impedance Z1 and Z2 which are equal to Z by 1 minus k and Zk by k minus 1, k being the value between V2 and V1. So, exactly from here we can immediately write down what will be the impedance values due to the capacitance in the two sides. So, input and output side. So, let us revisit that circuit again. In this circuit we are now going to distribute this capacitance CBC in the input and output circuits. So, for that we have to find out the impedance value of this CBC, and then correspondingly we can distribute it into the two sides, input and output, if we have the ratio of the voltage, that is k. K value is V naught by Vi, that is V2 by V1 means output voltage V naught by input voltage Vi, that is the two voltages are at these 2 points across which we are redistributing the capacitance. This point is nothing but having the voltage Vi, and this point collector is having the voltage V naught. So, let us do that. So, we are distributing this in between capacitance which was here CBC, that is this capacitance CBC is now divided into two Miller equivalent capacitances known as or denoted as CMI and CMO, Miller input capacitance, Miller output capacitance. So, what will be the value of these capacitances CMI and CMO, or rather what will be the corresponding reactances or impedances offered, that we can calculate. Others are all same. CBE is already there and it is not creating any problem since it is between base and ground. The problem which was created by CBC, because it was shunting between these two and we were not being able to analyze the circuit because input and output sides were not separated out, we will have to use this technique. So, now what will be this CMI and CMO and MO, we are going to find out. So, the voltage gain is V naught by Vi, and that we know this is the voltage gain AV. So, the input side will be having the impedance, and impedance due to a capacitance is equal to 1 by j omega C. So, here C is equal to CBC. So, the impedance offered by this in the original shunting part is 1 by j omega CBC, and we will be first of all finding out what will be this capacitance in the input side, that is we will be going to find out CMI, because following this Miller theorem which we have just now seen, in the input side it will be Z by 1 minus k. So, in the input side CMI will be having the impedance 1 by j omega CMI, that is equal to 1 by j omega CBC divided by 1 minus AV. So, we are just replacing Z is the value of the Miller's capacitance Z1, we are finding out which is equal to Z by 1 minus k. Here Z1 equal to 1 by j omega CMI, because when I consider Z I must find out the reactance or impedance, and that is equal to Z being the original capacitance which was j omega CBC divided by 1 minus AV, that is what is here, and that is nothing but 1 by j omega CBC into 1 minus AV. So, now we can find out what is CMI, these are same, cancel out. So, CMI equal to CBC into 1 minus AV. Similarly, in the output side, if I want to find out what is the value of CMO, proceeding in a similar manner, because we know that Z2 in the output side equal to Zk by k minus 1 or Z by 1 minus 1 by k, that we have seen here, Z by 1 minus 1 by k. So, putting that here, Z2 means 1 by j omega Cm naught we are going to find out, that is equal to 1 by j omega Cbc by 1 minus 1 by k, k is AB. So, from this we can cancel out. So, what is Cm naught? Equal to Cbc into 1 minus 1 by AB. So, now we can replace these values, find out what is Cmi and Cm naught. So, we will be having in our figure or of the amplifier two capacitances in the input side, because Cmi is there, already Cb is there, and the output side of course there is one capacitance. Now, we can combine these two parallel capacitors, because we know that parallel capacitances give the equivalent just by summing up. So, Cbe and Cmi can be combined together by summing up and writing it as Ci. Only one single capacitance I am writing by combining both of them, which is the input capacitance, and the output capacitance is Cm naught. So, now in this circuit, this is a simplified very easy circuit now to analyze or to handle. Now, we are going to find out what is the upper cutoff frequency. So, for that we have actually two capacitances. So, here also we will be considering one at a time. So, the effective resistance, if I find out for C1 from this side, what will be the effective resistance? Look from this Ci, there are three resistances in parallel, beta plus 1 Re, Rb, Rs. So, that will be the effective resistance, Rs parallel Rb parallel beta plus 1 Re due to Ci. So, the cutoff frequency due to Ci can be written as 1 by 2 pi into effective resistance into capacitance, that is the cutoff frequency due to Ci. So, 1 by 2 pi into Ci into effective resistance, Reff is nothing but this value. Similarly, effective resistance seen by capacitor C naught, which is nothing but CMO. If I look from this side into the circuit and look to find out what is the effective resistance seen by this capacitance, there are two resistances in parallel, Rc and Rl. So, that will be the effective resistance. So, effective resistance due to C naught is Rc parallel Rl. So, we can find out what is the cutoff frequency due to C naught, Fc naught equal to 1 by 2 pi into C naught into Rc parallel Rl. So, now we have the two cutoff frequencies, as earlier we have got in low frequency analysis also three cutoff frequencies we got and took the largest of the three. Here we will be taking the lowest among the two, because if we have a number of cutoff frequencies, we will be taking in the high frequency region the lowest value. So, now whichever is having the lowest value, that will be the cutoff frequency. Overall cutoff frequency is the smaller of the two cutoff frequencies. So, now in this analysis we have seen the lower and cutoff frequencies and how to find out this lower and higher cutoff frequencies we have analyzed. Now, from this we can now do one example to find out the lower cutoff frequency for this amplifier shown in this circuit. So, this circuit is having, this is the coupling capacitor, this is the coupling capacitor, this is the emitter bypass capacitor. We have to find out the lower cutoff frequency. So, in order to find out the lower cutoff frequency, we have to find out the effective resistance for each of these capacitances and then find out the corresponding cutoff frequencies, and out of all the cutoff frequencies which we obtained for these three cases, we will be taking the largest value. And in this circuit, this is nothing but a common emitter amplifier, and here R naught is equal to infinity is given to us. So, if we consider the equivalent circuit. The equivalent circuit will be having, first of all let us consider the capacitances together, all of them we will be considering, and this is a common emitter amplifier. So, we know that output side is having this current source, dependent current source beta IB, this is IB, this is beta plus 1 RE, this we are all familiar with, RE, CE, CS is the source capacitance, RS is source resistance, VS is the voltage at the input, that is the small signal at the input, RC is there, R naught is ignored, this is the coupling capacitor, and RL. This is the circuit, this is V naught. Now, this is RB, which is nothing but R1 parallel R2, because in this circuit, if we notice, this is a potential divider biasing circuit having two resistances in parallel. So, RB will be R1 parallel R2. Now, in this circuit, of course, here it will be, let us make it. So, now R1 parallel R2 is the base resistance RB. Now, in order to know this RE, as we all already have seen, we have to find the DC equivalent circuit, and from that only we can find out what is small r small e. So, DC equivalent circuit, if we consider, it is having resistances R1 and R2, and this is RE, RC, this is VCC is equal to 20 volt, R1 is equal to 40 K. So, we have discussed about the mid frequency region as well as the low frequency region and high frequency region for the signal which is applied in the input of the amplifier, and we have seen the voltage gain, how the voltage gain is not affected by frequency in the mid frequency region of the signal, but it goes down when we have the low frequency and the high frequency in the signal being applied. Now, let us do one or two examples. First of all, we will be discussing and we will be recalling our analysis for the mid frequency region, that is when the capacitive effects are not there. So, such an example let us take for a common emitter amplifier. You are to find out, in this figure shown is a common emitter amplifier where you have to find the voltage gain at no load and also the voltage gain at load and the input and output impedance and current gain. So, in this amplifier we have to first of all draw the equivalence circuit in the small signal analysis, and here to be noted is that there is no series resistance in the source, and we will be also not considering the R naught because R naught is not mentioned. So, we will be considering that the R naught is sufficiently high, like it is open circuiting. So, considering the signal analysis in the low frequency region, we will be doing this example. So, let us draw first the small signal equivalent model. So, here we have the common emitter amplifier, and at the output side the collector resistance and load resistance will be there, RL, RC, and this is the beta times of IB, which is the collector current, beta plus 1 RE, this is the emitter point, base point collector. RB is the resistance at the input, which is nothing but the parallel resistances between R1 and R2, and this is the signal which is applied, and this is Vi at this point, V naught is here, the input current is II say, and this is the base current. Now, in order to know what is RE, again we have to consider the DC equivalent circuit. The value of RL and RC are given, and the value of beta for this circuit is given as 100. So, now in order to know RE, let us consider the DC equivalent circuit. So, the DC equivalent circuit, if we consider, we have the resistances R1 and R2, and this is a common emitter circuit. It has RE, this is the RC is there, RC value is equal to given as 2.2 K, RE value is given as 0.75 K, R1 is equal to 68 K, and R2 is equal to 16 K. VCC is given as 16 volt. Beta is equal to, for this amplifier, beta transistor value $100. So, beta is 100. Now, in order to find out this RE, we know that we have to find out capital I capital E, because 26 millivolt by capital I capital E, that is equal to the RE. Now, in this DC equivalent circuit, in order to know what is the emitter current flowing, we have to draw this Thevenin's equivalent across this base to ground, and that will be given by a parallel resistance R1 and R2 and a Thevenin's equivalent resistance R Thevenin, V Thevenin is equal to VBB say, which is equal to VCC into R2 by R1 plus R2. So, VCC in this case is 16 volt, R2 is 16 K, and R1 is 68. So, 68 plus 16. So, that is equal to 3.05 volt, and R Thevenin, which is equal to say RBB, I am denoting by R Thevenin by, and that is equal to R1 parallel R2, that is R1 into R2 by R1 plus R2. So, R1 value is 68 into R2 value is 16, 68 plus 16, and that comes to 12.95 kilo ohm. So, now we can find out what is the emitter current in this circuit. So, if we consider the circuit, we can draw it like this is VBB, which is V Thevenin, RB, that is R Thevenin. These values are 3.05 volt and RB is equal to 12.95 kilo ohm. And then we have this side is having this resistance RE, which is equal to 0.75 kilo ohm, and RC is there, which is equal to 2.2 kilo ohm, and this VCC is 16 volt. So, this current we are interested in finding out IE. So, we know I is equal to beta plus 1 IB. So, now if we consider this input side, the current which is flowing is, here is IB, here is IC, and here is IE. Now, VBB minus IB into RB minus VBE, base to emitter drop, minus IE into RE, that is beta plus 1 into IB into RE, that is equal to 0. Replacing the values, 3.05 minus IB we have to find out. So, taking common RB plus beta plus 1 RE minus 0.7 is VBE, we have to take 0.7. So, now what is IB? IB equal to 3.07 minus 3.05 minus 0.7 divided by RB plus, RB is nothing but 12.95 plus beta plus 1, beta is 100 for this transistor. So, 100 plus 1 into RE value is 0.75. So, that gives IB value to be 0.02651 milliampere. So, we know now what is the value of IB. So, we can find out what is the value of IC and what is the value of IE. So, IC is equal to beta times of IB, and IE value can be found out to be beta plus 1 IB. Putting the values of beta 100 and IB is equal to 0.02651, we get 2.677 milliampere. This is IE. So, now we can find out what is small RE, 26 millivolt by capital I capital E. So, 26 millivolt by capital I capital E is 2.677 milliampere. If we calculate this value, it comes to 9.71, this much ohm. Now, after this we can find out the required parameters like AV no load. Now, if we want to find out what is AV no load, that means without this load, if we do not consider this load, what will be the voltage gain with respect to V naught and Vi. So, V naught by Vi, if I now calculate V naught, what will be V naught? V naught is equal to the current which is flowing through RC multiplied by RC. The current which is flowing through RC is beta times of IB. If we do not consider RL, that is called no load. We are ignoring the load, means we are having only up to RC. RL is like open circuited. So, this is called no load voltage, that is V naught by Vi is equal to minus I naught by RC, I naught into RC by IB into beta plus 1 RE. Because if we look into the circuit, the Vi is equal to IB into this resistance beta plus 1 RE, and the current which is flowing through RC is the same current beta IB, which is nothing but I naught, because I naught will be now same as IC without load. So, multiply it by RC, that gives the output voltage, and I naught is nothing but beta times of IB. So, minus beta times of IB into RC by IB beta plus 1 RE. So, we get minus beta RC is equal to minus 100, RC is 2.2 K, and beta plus 1 100 plus 1, and RE we have found out to be 9.71, but this is in kilo, this is in ohm. So, we have to convert it to kilo ohm, and this gives the value of minus 224.33. Now, this is no load voltage gain. If I consider load V load, so this value of V naught by Vi will be minus I naught into RL by denominator will be same. So, finally, I naught can be written as beta IB into that part of the current which flows through RL, and that is beta times of IB into RC by RC parallel RL into RL by IB into beta plus 1 RE. So, this value when you put it, it will be equal to minus 100 into RC value is 2.2, RL is 5.6 kilo ohm by 100 plus 1, and RE value is 9.71 into 10 to the power minus 3, and that value is equal to minus 161.06. So, now if we just see that when it is with load, the voltage gain reduces because of the fact that now the resistance RL, the load will be in parallel with RC. So, the equivalent resistance at the output will be reduced. That is why we are getting a lesser voltage gain than without load. Now, what is input impedance? That is known as Vi by II. Vi is IB into beta plus 1 RE, and II in the denominator. So, IB can be again written as, if I look into the circuit, IB is equal to II into RB by beta plus 1 RE. So, putting this value II into RB by RB plus beta plus 1 RE by II into this small RE will be there. So, now this is equal to RB into RE by RB plus beta plus 1 RE. So, that will be, oh, here it is left this beta plus 1 RE, sorry, this is beta plus 1 RE, because I am writing IB with this quantity and beta plus 1 RE is there. So, this is nothing but RB parallel beta plus 1 RE, and if you find out this parallel impedance of 12.95 and 100 plus 1 into 9.71 into 10 to the power minus 3, that comes to 0.91167 kilo ohm. So, finally, we get that it is 91.17 kilo ohm. Similarly, if we want to find out what is the output impedance looking from this point, that is nothing but only RC. When you make this Vs is equal to 0, this IB will be 0, it will be open circuit, we are left with only one resistance at the output, and that is equal to RC. So, the value of RC is equal to 2.2 K ohm. So, the output impedance is 2.2 k ohm. So, in this circuit whatever we have considered is an amplifier circuit having no effect of capacitance, that is we are considering only in the mid frequency region, and we are finding out the voltage gain and other impedances like input and output, and with no load as well as with load. But that will be not the same analysis if we consider it in the lower frequency or higher frequency region, because this voltage gain whichever we have found out, it will be not the same, it will be reduced.